Welcome back to our journey into deep learning. We've met the single neuron, the perceptron. But how do we go from that one simple building block to the incredibly powerful networks that drive modern AI? Today, we dissect the anatomy of a neural network. The key takeaway from the perceptron was its limitation. It can only solve problems that are linearly separable. The brilliant solution to this is not to build a more complicated neuron, but to connect many simple neurons together in a structured way. Just as a single brick is limited, a wall of bricks, arranged in layers, is incredibly strong. This layered structure is the core concept of a neural network. At a high level, every neural network is composed of three types of layers. First, the input layer, which receives our data. Second, one or more hidden layers, which form the computational brain of the network. And finally, the output layer, which delivers the final prediction. The flow of information is always forward, from input, through the hidden layers, to the output. Let's look closer at the input layer. Its job is incredibly simple. It receives the raw data. There is one node, or neuron, in this layer for every single feature in your dataset. If you're predicting house prices from size and number of bedrooms, you'd have two input neurons. This layer performs no calculations. It's simply the entry point, like the sensory organs of the network, feeding it information about the world. Next are the hidden layers. These are the layers sandwiched between the input and the output, and they are the true computational core of the network. Each neuron in a hidden layer is connected to all the neurons in the previous layer. It takes their outputs, computes a weighted sum, and applies an activation function, just like we've learned. They're called hidden because they have no direct contact with the outside data. They only see the transformed outputs from the layers before them. The number of hidden layers and neurons, the network's architecture, determines its power. Finally, we have the output layer. This is the last layer of the network, and its job is to produce the final prediction. The structure of this layer depends entirely on your goal. For a binary classification problem, like spam or not spam, you might have a single output neuron. For a multi-class problem, like identifying handwritten digits from 0 to 9, you would have 10 output neurons, one for each possible digit. This layer represents the network's final conclusion. The lines connecting the neurons are just as important as the neurons themselves. Each connection carries a weight, which is a number that determines the strength of the signal. A high weight means the signal is amplified, a low weight means it's diminished. The entire process we call training a neural network is nothing more than a systematic algorithm for finding the perfect values for all these millions of weights and biases, to make the network's final output as accurate as possible. These weights are the learned knowledge. So there you have it, the complete anatomy. A neural network is a system of simple neurons organized in layers. Data flows forward, from the input layer, through the computational hidden layers, to the output layer, which provides the answer. This hierarchical structure allows the network to learn simple patterns in the early layers and combine them into incredibly complex concepts in the later layers. Now we know the structure. But what exactly is that activation function inside each neuron that gives it its power? That's our topic for the next lesson.